Hello, welcome to the online course NICER 201 on causal inference from observational studies. In this session, we'll talk about famous p-values. I have divided this session into three parts. In the first part, I'll talk to you about what your p-value is. The second session, we'll look at how do we interpret p-values. And in the third session, very importantly, we look at some of the common misinterpretations of p-value that are found in literature. So let us go directly into the first session on what is p-value. In order to understand p-values, we need to understand how we do statistical analysis. In the inferential statistics, we usually take a sample of study participants from the population through several methods of selection of these study participants. We get a sample of them and we do our experiments, we do our measurements of exposures, outcomes, covariates, etc. on this sample of study participants. And whatever results we get, we try to then infer from this sample what the actual values or the true values would have been in the entire target population. For the purpose of this, we use what is called as hypothesis testing. Hypothesis testing is generally used when a comparison is to be made. Comparison between the study population and maybe the entire target population, or comparison between two groups where one is exposed and the other is not exposed, or one has the outcome and the other doesn't have the outcome, or it could be comparison amongst multiple groups as well. The choice of which statistical test to use depends on the format of the data as well as the study design. In hypothesis testing, any observed difference that we get between these two or more groups are interpreted within the context of a null hypothesis. More formally, hypothesis testing explores how likely it is that the observed difference would be seen by chance alone if the null hypothesis were true, and the end result of any statistical test is a p-value, where p stands for probability. So then what is p-value, or how do we define p-value? As I mentioned in my previous slide, we start off with postulating a null hypothesis. Some examples of null hypothesis, for example, if we are trying to look at whether MMR vaccination could be a risk factor for autism in children, we would state the null hypothesis as MMR vaccination does not affect a child's subsequent risk of autism. If we're trying to study the relationship between birth weight and, say, IQ as an adult, the null hypothesis would be that birth weight is not associated with the subsequent IQ. We're trying to assess the relationship between, say, power lines and children's risk of leukemia. Our null hypothesis would be living close to the power lines does not change the children's risk of leukemia. And then we estimate the risk of leukemia or the IQ or the autism. We also look at people, whether they were vaccinated or not, whether the birth weight was above or below a certain level, how close or far people were living from these power lines. And we try to do certain statistical tests and we get a value which helps us to tell whether the data in our sample provides evidence against this null hypothesis. So formally speaking, p-value is the probability of the observed result, that is the observed value of the test statistic, plus more extreme results if the null hypothesis were true. We do have a definition here, but I'm not sure how helpful this definition actually is in actually knowing what a p-value is and how to interpret this p-value and how to avoid any misinterpretations of the same. So we'll go more deeper into and try to understand what actually this definition means. In order to interpret p-values, the p-values, since it is a probability, it ranges from a lowest level value of 0 to the highest value of 1. A smaller the p-value, we can say that lower is the chance of getting the difference as big as the one that was observed in the study, assuming that the null hypothesis is true. And therefore, a smaller p-value provides a stronger evidence against the null hypothesis, and a larger p-value, henceforth, provides a weaker evidence against the null hypothesis. So as the p-value increases from 0 towards 1, that shows that there is actually decreasing evidence against the null hypothesis. Now, in order to get a bit more better understanding of the use of these p-values, we'll need to go back into history. The confusion that exists in today's practice of hypothesis testing and the interpretation of p-value actually dates back to a controversy that raged between the founders of statistical inference more than 60 years ago. P-value, as we know it today, was first formally introduced into the world of statistics by Carl Pearson. It is Pearson's chi-square test, where he used the chi-square distribution and gave the notation of p-value as capital P. His contemporary was R.A. Fisher, who's also known as the father of modern statistical inference, and he's the one credited with introducing the idea of significance levels as a means to look at the discrepancy between the data and the null hypothesis. Essentially, how to use p-values to generate evidence against or for the null hypothesis. According to Fisher, he saw p-values as an informal index to be used as a measure of discrepancy between this data and the null hypothesis. In his own words, null hypothesis is never proved or established, but is possibly disproved. Further, he advocated a level of 5% as a standard level for concluding whether there was evidence against the test hypothesis that was tested or not. This was a subjective interpretation of the p-value, and a dislike of this subjective interpretation, which was inherent in Fisher's approach to using p-values, led another set of statisticians, Niemann and Pearson, to propose what they called as hypothesis tests. These tests were designed to replace the subjective view of the strength of evidence against the null hypothesis provided by the p-value with an objective, decision-based approach to the results of studies and experiments. In fact, Niemann and Pearson argued that there were two types of error that could be made in interpreting the results of any experiment, type 1 error and a type 2 error. And in the Niemann-Pearson approach, we decide on a decision rule for interpreting the results of our studies in advance. And the result of our analysis is just a rejection or an acceptance of the null hypothesis. If we go a little bit more into how this value, this threshold of 0.05 came into being, what we find is that Fisher, when he was writing his book on statistical methods for research workers in 1925, and he wanted to provide p-values and chi-square tables and the related p-values in his book. And since Carl Pearson, his contemporary, was the one who had introduced chi-square tables, he requested Carl Pearson to reproduce the Carl Pearson's tables. But Carl Pearson refused. And since now that Fisher did not have the exact values of p-values for each of the chi-square values, he decided to tabulate the p-value results. So you have 0.1, 0.05, 0.02, 0.01, and so forth. And that's the way he produced his own tables. And that is what you would see in most of the statistical tables that you have in the standard textbooks. In fact, Egon Pearson, who's responsible for the hypothesis testing, he in fact later acknowledged Fisher's decision of why he tabulated the p-values in this way. So the Niemann-Pearson actually used this cutoff of 0.0 to make that decision of whether something in line with the null hypothesis or against the null hypothesis. So here we see that over time, there were actually two mutually exclusive approaches to using the same parameter called p-value. Fisher had a more subjective approach where he suggested to use cutoff as a guide to understand the strength of the evidence against or for the null hypothesis, whereas Niemann-Pearson had a decision theoretic approach where they actually made a cutoff between a level where we could decide whether this was statistically significant or not. This decision-based approach was something that was useful from an industrial point of view, because at that time, again, remember that so America was going through a kind of an industrial revolution during the 30s and 40s. And even in the industry, it was good to use. So if you had, say, 100 products being manufactured, and if you found a batch of 100, for example, and then if you found that more than 5 of these products had some defect, you could reject that entire batch and instead of checking for each of the 100 articles. And if you had less than 5 or equal to 5 products which had some defect, you could still let the batch go as with minimal defects. Henceforth, since that time immemorial, we have been so using this decision theoretic approach in the form of hypothesis tests in our studies and to interpret the results of our study. So then, how exactly do we understand what p-value is? The p-value can be viewed as a continuous measure of the compatibility between the data and the entire model used to compute it, not just the null hypothesis, but all the other hypotheses as well. As we've seen, as a probability, it can range from 0, or if your p-value is 0, that means your data is completely incompatible with the hypothesis that you are testing, to 1, where the data is perfectly compatible to the hypothesis that you are testing. And in this sense, p-value may be used as measuring the fit of the model to the data, and nothing more and nothing less. In the next session, we'll go more in depth into practical ways of interpreting p-values. Thank you.